of that law. Now, what does it really mean? Remember, this one, we found high degrees of symmetry, and you could figure out what D was, right? Typically, if we had a surface charge over a spherical surface, this would be 4 pi r squared times D was a charge enclosed, which is typically the integral of the charge density over the volume enclosed. Do you all remember that? Over here, we're going to do something under here where, and I'll apply it to this law. Now, if you have something where it's a high degree of symmetry, for instance, cylindrical symmetry, this is the most common one. Let's just assume I have just an infinite filament of current I. And I come out, a given radius, say rho, and I put a loop of wire around there. So I'm trying to make this look like it's in the XY plane. But this is X and this is Y. This loop, not loop of wire, a loop of, it's called an Amperian loop here. And I take a look at this. If this is an infinite current, now this is where you have to have some amount of common sense, really an understanding of the phenomenon. If you've got an infinite current, remember I told you if you use your right hand and put your thumb in the direction of the current, your fingers curl in the direction of the H field. Do y'all remember that? For each one of these points, you're going to get an H field that will be symmetric. And it will be, really it'll be in the azimuthal direction. So if I apply that law to this event, and I'll do it here, then I get this. It's an integral of H dot dl around the closed loop. And do me one favor, this is in the counterclockwise direction. Looking, it has to be in the direction of the positive surface integral, is equal to the I enclosed. All right, now, when I look at this one, for this Amperian loop here, I started with just a current in a straight direction. All right, the integral of H dot dl here really is going to be the H field in the phi direction, and the integral of dl, well, what is the actual differential, what is the actual total length around here? If you integrated dl around a closed loop, what's the perimeter?
2 pi r, or 2 pi rho.
2 pi times the radial distance, exactly right. It's 2 pi rho. And that's equal to the charging or current enclosed. That's just I, if I have a single filament. Do y'all follow me on this? Therefore, H of phi is equal to I over 2 pi rho. Now, do you remember when we got this, when we had the differential form of the current? Think about this. I had an I dl here, and I ended up getting a dH here, and then I had to integrate that dH over the entire existence loop to find the current. To find the H field. Do you all remember that? That's a pain. Same thing with how Gauss's law that I erased. It makes problems with a high degree of symmetry. It makes the calculation of the E field or D field trivial if there's a high degree of symmetry. You can integrate the integral of D dot ds, set it equal to the charge enclosed. Assuming there's a high degree of symmetry, you can get the D field / E field, either one, right? If you got D, you have E if you have epsilon, right? Here, I can get the H field without doing any crazy, integrations over contours or over links. Do y'all follow me on this? That's easy. Now, for this one, I'm going to tell you something. This problem, it requires a bit more understanding than probably, I'll just tell you this right now. If you had a solenoid and you had a whole bunch of turns of wire, if I just had a solenoid like this, and I wrap it with wire, whole bunch of turns. Remember we went through and we talked about if it's wrapped with turns and you have n turns, and you look at the center of the solenoid, the H field will always be in the z direction. You always have an H of z. Do y'all remember that? We did it. We start with a single loop, right? If we're on the z-axis and that loop's symmetric, right, centered on the z-axis, then the H field at z equals 0 is straight up or straight down, depending on how the currents go. Now, if that's the case here, take that solenoid and just bend it around. This is the one thing you have to see. The H field, if this is tightly wound, the H field will be in this direction. It will be along the axis of the actual toroid. Do y'all see that? Now here's the part you have to pay attention to. So now I'm going to take this, and I'm going to say that I'm going to make an Amperian path. I think he does it this way in the book. This is a classic problem. They may have done this in physics. I don't remember if they did it here. And I'm going to say this is my Amperian path right here. And I'm going to make the case the H field will be the same anywhere along this. It's not a function of the angle, you know, if you think about phi. You all with me on this? If the H field is a constant there, and it's in this direction, then I can say the integral of H phi dl, well, technically it's H dot dl vector around this closed loop in the counterclockwise direction is going to be equal to the amount of current that penetrates this. Now this is going to be a little hard to see unless I expand this, so I'm going to expand it right here. You see it. So assume we have this toroid with a whole lot of turns, and we just cut it right down the center, and we look at what it looks like. So you're going to have this, and then you're going to have a whole lot of kind of right down the center. We're going to have all these, what do we want to call them? Current filaments, and they'll be going in here and then out on the outer part, but there would be also these adjoining where they would come in, or coming out of the board into the board, depending on how the current's flowing. This isn't going to matter for this one. Are you all with me? Now, each one of these has a current I. That means if I take a look at this and I do my integral, when I take a look at the integral of H dot dl here, I'm going to do it right there. And I'm going to say there's a condition that rho itself is greater than really the radial distance b minus a, and it's also less than b plus a. In other words,
In this problem, A is defined as the inner radius, B is the
mean
central
radius, I
and C
think.
is the outer radius.
Oh, C is the outer radius?
Yes.
All right, so we go between C and A and C. In other words, it's between here and here. You all with me? Now remember, I cut it. So when I take a look at this integral of H dot dl around here is going to be really just 2 pi rho times H phi. That's all it is. You all with me? I'm going to go around there. Rho is between A and B, A and C, I should say, right? That's equal to the current. How much current is penetrating this loop? And this is the area of the loop. It's this entire thing here. Well, it's I times the number of turns. So it's going to be Ni. So that means H phi in between, or when you're inside the solenoid, or toroid, is just equal to Ni over 2 pi rho. And that is it, and it's amps per meter of the units. But this is the H field. Now that's between. What else does he ask?
Then it says find it at B, but then you replace rho with B, and that's it.
Find what? The B field?
Find the H field at B,
Just put.
and then you just replace it with a B, and then that's it. That's all.
You all with me on this, guys? Now, since I'm up here doing this, I want to just add something. You remember before when you had electrostatics, you had a relationship between between D and E, and D was equal to epsilon E. Y'all remember that? That's a simple relationship that includes the material constant. For us, there's also something called the B field, and that's equal to mu H. Now mu is mu relative times mu 0, and mu 0 is 4 pi times 10 to the minus 7th, and that would be henries per meter. This is exactly analogous to this. This is a relationship between a B field and an H field. Now the B field, the typical units of B field, I mean, there's a couple, but is either Webers per meter squared or it's Tesla. Either one, they mean the same thing. Y'all with me, class? I know you've seen the B field before, but the B field become important because that's the thing. When we want to know the force on an actual piece of current or a lot of magnetics, it's the B field. It's IDL, differential current times DL, crossed in the B field gives you the differential force. I'm going to say that way because remember, for the force on a piece of charge, it was just what? QE, right? Or Q times, and then E would be D over epsilon. Here, the force you'll see is related to the B field, not the H field, even though it's related by the constant U. But we'll get to that later. Any other part of that problem? Is that it?
I'm good.
Y'all, do you remember seeing problems like that?
Yes.
Okay, that is Ampere's law applied to that problem. Now, we might as well do at least one or two other examples of Ampere's law before we move on. And in physics, I don't know what level of complexity they got into, but you've had Ampere's law, and you've had Gauss's law, and you've had the Biot-Savart law, and you've had Coulomb's law. You've had all of this stuff, but it's usually at a reduced level of complexity. They don't try to make things that difficult. So, now for a few problems.
I think another Ampere's law you signed was 417.
Yep. That was the only
Why don't
other
you tell me 417?
Okay. It says, given a 3 millimeter radius solid wire centered on the z-axis.
Hold on. So we got A is 3 millimeters. Go ahead. On the z-axis.
With an evenly distributed 2 amps of current in the AZ direction.
Okay. So we have I equal 2 amps going up in the z direction. Everybody follow me on this?
Yeah, it says plot the magnetic field intensity
Versus
intensity
distance
H versus the distance over the z-axis.
Here's rho, and they want to know.
They want to know range from 0 to 9 millimeters.
That's fine. All right. For a problem like this, first you all agree it's a high degree of symmetry. If you look at this problem, all the currents go in that direction. And logically speaking, if you come out any distance rho and did that loop that I call the Amperian loop here, then the integral of H dot dl over that closed loop has to be the I that's penetrating the surface area of that loop inside it. Are you all with me? Okay. So what I'm going to do is first back up a step, and instead of having a current of 2 amps, I want the current density J. And since that's uniformly distributed, I take the current I and I divide by the surface area A, and it's in the AZ direction. Y'all follow me on this? So that means J itself would be equal to I, and it doesn't matter the value, over pi A squared AZ, and the units would be amps per meter squared, and that would be J, that would be the current density. All right, is everybody with me on this? Okay. Now, I go ahead and I'll try to show you. Now I'm going to make my Amperian loop like right here at a given radius rho, and I have to do one thing, I have to qualify the range. So I'm going to say when rho is less than the radius A, and I go ahead and I say the integral of H dot dl around the closed loop is equal to the current inside of it. Well, that's technically a double integral of J dot ds over the surface enclosed by this loop. Do you all follow me?
Yep.
You with me on that? You think about it, if you look straight down here, we're out at a distance rho. Here's my loop. I know the H field is this way. So the H field integrated over that loop is simply 2 pi rho H feet, and it's equal to all the current penetrating in there. Well, that current right there, because the current density is a constant, you can just take this current density times the area. Now, if it wasn't constant, it was a function of radial distance, then you'd have to perform the integral. This one, for anything that's circularly symmetric or cylindrically symmetric, this will always be 2 pi rho times h phi. It's just the perimeter or the circumference times h. Do y'all follow me? It's equal to this. Well, technically, what you should do, if you want to do it right, is say it's j, in this case in the z direction, AZ, and it would be dotted into the differential surface, and that would be rho d phi d rho, and the AZ direction, and then you would do the integration, and phi would go from 0 to 2 pi, and rho would go from 0 to rho, and technically I should prime that, but you all follow me. Now, for us, j is a constant. So really, since j is a constant, I can take it in front of there. Az dot az is 1. And what I've got there is the differential area. When I integrate it over the total area, it's just the area, which is pi rho squared. Do y'all follow me? So that means, I'll do it here. When I take a look at this, now I have 2 pi rho h phi is equal to, on this side, you get simply jz, or really, I'll just call it I over pi a squared. That's simply jz, and it's times the area of inside that loop. And that's going to be equal to pi rho squared. Y'all agree with that? So if you take a look at this, you can see that this becomes really I, and it's ratio. It's rho over a squared is equal to 2 pi rho h phi, or h phi is this divided by 1 over 2 pi. And it doesn't matter the form it takes, but you all with me on this class? So that's the h field. I got a question for you. Where's the h field, the maximum inside the wire? This is, inside that wire. This is for rho less than a, greater than 0. Just look at it. Where is that largest?
Near the center.
It's centered 0, right?
Wait, wrong thing. Sorry, at the edge.
That's right. When rho is at its maximum at a, and at a, it's going to have a value of what? I over, this should be a rho here. This should be a rho. So it's just going to be I over 2 pi rho. Isn't that what it is from an infinite wire? Yeah, as a matter of fact, that's exactly what it looks like. Now, when you get outside of where the wire exists, remember, now we're going to be, or where all the current density exists for rho greater than a. When you look at Ampere's law, the integral of h dot dl around that closed loop is still equal to the I enclosed, right? But now, if I'm out here, right, rho greater than this, well, all the current is limited to the inside of that wire, right? And it is I. Do you agree with that? So that means over here, when I do this, now I get 2 pi rho h phi is just equal to I, and h phi is equal to I over 2 pi rho, and this is for rho greater than a. So if you plotted this, and I will ask you to sketch this on quizzes and on tests, especially the final exam, I ask for a sketch. So if you sketch that, here's rho equal a, and here's 0. And you look at the h field, well, what does it do? Hits the peak value here. This is simply going to be I over 2 pi a, and then it goes down. That's 1 over rho. Can you all follow me on that, class? And this will be your h of phi as a function of distance. Now, what can happen that's a little different, and I want you to hear me now. This current does not have to be a constant. In other words, he said it's evenly distributed. I could give you J, and J could be a function of the position, how far out you were radially. You all follow me? Then you would have to do this integral right here formally, and you would have to do it. You okay with that, everyone? And you get the idea. Just like with when we had the problems where you had charge distributions. If charge was uniformly distributed, no big deal. Just take total charge over the volume, that's the charge density. But if it's a function of radial distance, then you had to go through the integration to get the d field. You all remember?
Yeah.
Okay. So that's that one. Now,
Is that due to the skin effect, or is that a completely different thing?
I'm defining what J is. Skin depth and things like this have to do with frequency variation. This is DC.
Okay.
So if I define what J is, in other words, you don't know how it's that way, you know it's that way, though, then you use this. Skin depth is AC. It's further down the line. All right, now, next. Do you have another one for me?
I can. Do you want another Ampere's law? Or
Yeah, I want to, because the way in my opinion, you can talk about theory all you want. Until you see it applied, a lot of times it doesn't make a whole lot of sense, especially abstract concepts.
That's the only one you assign. You want me to just pick a
Yeah.
random one?
Go ahead and pick one.
What do you want to do? I don't know.
4.22.
All right, you need to erase this, not yet.
Sure. It works.
Ampere's law is, it's one of these things, you've got to see it, you apply the problems to really appreciate it. I mean, a lot of this mathematics, you talk about curl divergences, Laplacians, gradients. Well, gradients are a little different, that's just a directional derivative, but they're obscure unless you see them applied. Go ahead.
Consider a pair of collinear.
Which problem is this again?
4.22.
Go ahead.
Consider a pair of collinear cylindrical shells centered on the z-axis.
Okay, so we got a z-axis here, and we have shells. That means you got some inner radius A, and it's just a shell like this, and then an outer radius B. I'm just picking these.
That's the same as in the problem.
Okay.
Inner shell has current I in the plus AZ.
Okay. He's saying that on this one, it's going, I is uniformly distributed all over that inner. It's just you said it's a shell. It's really just a thin piece of metal. Think of it.
Yep.
But I's on that one, and it's coming back on this one, right?
Yep. And so it wants you to plot the
H field
H
versus
field.
radial distance.
from 0 to 2 times b.
No problem. All right, now, here's the way I'm going to talk about this one. If you look at this and look right down the z-axis, you see this. You'll see this, basically. Now, all the current, if this is the z-axis coming out of the board, you can call this x, y. It really doesn't matter. X, y, and this is z coming out of the board. If you take a look at the possibilities, there's really 3 regions. We're going to say for the radial distance rho, less than this inner radius A, less than A, okay. When we have that, I want you to notice this. This is important. We'll come over here. I'm inside this radius, right? There's my Amperian loop. So I'm go ahead and make an Amperian loop there at some radius rho. And I know that the integral of h dot dl around that Amperian loop has to be the I enclosed or penetrating that loop. Well, how much current is penetrating this loop? Remember, this is a symmetric loop. Any? It's 0. What's the H field?
0.
Exactly. So the H field, h phi times 2 pi rho, is 0, and that means h of phi is 0 inside. Now, I think you can see where I'm going. Next, this is going to be for rho greater than A, less than B. Now, I'm in this region. Here's A, here's B, and I'm out here. My Amperian loop will still be the integral of h dot dl around the closed loop right here, I'll get out of your way in one second. H dot dl. Around the closed loop is still the I enclosed, right? All right. Now, I'm somewhere greater than A, less than B. How much current is actually present? Well, it's all the current on radius A, right? Which was, I'm trying to show you this is A, right? So, because I'm out here. Follow me, class? So it's just I. That means out here I have I, and here it's going to be 2 pi rho h phi, or h phi is equal to I over 2 pi rho. And this is true for rho greater than the inner, less than the outer. Finally, when I'm outside, when rho is greater than B, now just think about this for a second. Now, try to draw it right here. Here's A. This is radius A. Here's radius B. All the current is coming out, you might say, here. But this is the z-axis. But it's going in here, right? In other words, the same amount of current that came out this way is going in on the outer radius. Do y'all follow me? So when I get outside there, and my radial distance is greater than B, how much current is penetrating this loop? It's a net of 0, right? All the current going this way is negated by the current coming out. You all follow me? So think of just a normal transmission line or coax cable. Whatever flows one way, the same amount in an opposite direction flows on the outer shield. You all with me on this? Same here. That means for this part, for rho greater than the outer radius, the H field is 0 because there's no current enclosed. There's no net amount of current penetrating that loop. You all with me? And that's it. So if you plotted this right here, it would be 0 from 0 to A, and it would jump up, and this is the H field you're plotting, it would be I over 2 pi A, right here. So basically it's 0, jumps up, and it asymptotically starts decaying until you hit B, and that current there would be I over 2 pi B, and then it goes to 0, that's it. Everybody with me?
Yeah, this might be a dumb question, but why is it 0 when it's less than A? Is that just because it's always 0 within?
No, think about the law, what it says. Here, I'm inside A, right? If you put this ampere in a loop there, how much current's penetrating that surface? Can you see that?
Yeah, that's what's wrong with this. It's just, it's going to be the net.
There's no current, right? The current is right here.
It's a shell. It's not a.
It's all on the outer edge. It's not evenly distributed. So it's basically like on the shield of a coax cable. You got an inner shield, outer shield. It's all at that point. So until you get out a radial distance past where that current starts flowing, you got 0.
Okay.
That's
So
it.
since there's a shell, there's nothing inside.
Yeah, it's really, think of it, a very thin piece of metal, and on the inside, very thin piece of metal on the outside. Same amount of current flowing up on the inner is flowing down on the outer, and that's what it looks like. I hope that, you got another one for me there?
Sure, we keep doing it.
Why don't you, go ahead.
We can do 421 if you want.
Take a look for a second, just gaze through there, see if you guys see a complicated one. Or something that confuses you. If you want 2-1, we'll do it. But
Actually, can we do 420 with I think it's instead of a shell, it's a shell that's like thicker.
okay, we'll do that. And you're going to see it's the same basic concept, just applied. You always find the amount of current that is inside that radius of the loop, and then set it equal to 2 pi rho. Most of these problems, almost all of these problems, are cylinders for this long. Almost. There's maybe 1 or 2 exceptions.
Would it be much different if it were, like, say, applied to, like, a spherical? Or would it be the same?
Well, how are you going to get the
concept?
spherical symmetric distribution, right? If the current's all flowing outwards,
Yeah, I guess that'd be kind of weird.
I can just tell you this,
Because it has to go in, like, a direction.
and I'm going to say this, I don't want to get too far ahead of myself, but I might as well say one. Suppose I have an inner radius A and an outer radius B, and this is a sphere, and it has some conductivity sigma, it doesn't matter. And now I drill a small hole, and I connect the wire there, and I say it's insulated, assume that has a current I there, and the current is uniformly distributed, and it flows out to this part, the grounding thing. So everything that flows in will flow out and be uniformly distributed on the outer shell. Basically, it's a spherically symmetric charge, or current. So you'd have current this way. The actual current density, J, would be equal to I over 4 pi r squared AR, amps per meter squared, right? Think about the Gaussian surface. How are you going to get a Gaussian surface that encloses anything? Well, you could say, well, what if we do this? Just put a loop there. There's nothing symmetric there. You all follow me? As a matter of fact, I can tell you the answer. If I ask you for the H field anywhere inside here, and I tell you that it's spherically symmetric, or basically that the current is going to be flowing in a way that it's spherically symmetric. There's no density difference at a given arm, no matter what your angle is, theta and phi. This H field will be zero always. Now, the reason I'm saying this, you can make a spherical capacitor like this. You can go ahead and you can put a dielectric here, and you can put a very thin lead in here and charge this inner center and ground the outer center, right? When you go to discharge this, you will have no inductance, no inductive energy stored there. It discharges very fast. It's limited by the inductance outside that loop, or outside this capacitor. I'm just telling you this for the record. So you may see something like this. It'll be a very, very thin shell. It'll be like something like this. See this? And then right above it, almost the same, is going to be another shell. Now they'll charge this one, and then they can discharge it. Now the problem with this always is you can't store much energy on these. You can't, you would like multiple layers, but it doesn't work that way. I don't want to go there, but that's why spherically symmetric things don't work. And the only other one that does work, if you have an infinite plane, you can actually, and I'll just do it right here. Suppose I have an infinite plane, and it's got a surface current. Let's say it's going into the board, and this has a surface current where it's K, and K would be in amps per meter, the units that, and I'm just showing you it going into the board. I'm going to make it real simple. You follow me on this, guys? Now, if you do this one, remember, and I'm going to take a section of length L, and if I do an Amperian loop here, and make these sides the limit as this height H goes to 0, now just look. My right hand tells me if it's going into the board, the H field would be in this direction above it, and below it would be in this direction. Y'all follow me? I'm trying to make this little, very small rectangle. It's got a finite length, but an infinitesimally thin distance. And it's enclosing that current. Well, the amount of current penetrating that, right, would be, the amount of current would be equal to K, the current density, times the length L. And that's equal to the integral of H dot dl. Well, kind of going into the board, this is the direction of the H field. Well, the integral of the H field from here to here is H times L. From here to here is H times L. So it's going to be 2 times H right here, or 2 times L. 2 times L times H. And you can see that that means that the H field is simply the current K, current density, divided by 2. Do you remember me talking about this? When we had the infinite sheet of current and we figured out what the H field was below it and above it? No? All right, now, here's the catch on this one.
Oh, yeah, no, I heard, yeah.
All right, this is important. Use your right hand, put your thumb in the direction of the current. Your fingers will curl around the direction of the H field. The H field is not a function of distance away from the plane, simply where it is with respect to the vertical point. If it's below this, the H field will be going this way. If it's above it, it's this way, but the magnitude is K over 2. Y'all follow me? That's a real important thing to know for a thin sheet like that. People often make these problems so complicated, but this is useful information too. All right, now which one did you want to? I'm trying to just throw some stuff out that I think is going to be very useful in the future. By the way, I have to take care of your exam. I've got to get from Mary. I'm great later. I'll get it to you on Friday. All right? Go ahead.
We'll just do 420. It says a cylindrical pipe with a 1 centimeter wall thickness and inner radius of 4 centimeters. It's the center on the Z.
Cylindrical pipe with an inner radius of what?
Inner radius 4 centimeters and outer radius of I guess 5 centimeters.
What is it?
5 centimeters.
Okay, so B is 5 centimeters, 1 centimeter thick.
Yeah.
Good.
This is center on the Z-axis, evenly distributed 3 amps of current in the plus AC direction, and I want you to plot magnetic field intensity H versus radial distance.
No problem. They got a total current of how much again?
Evenly distributed 3 amps of current.
Okay, now, y'all told me that all the current is limited to this shaded area, right? All of it is, right? It's in the Z direction. You give me that, everyone? So now we need the current density. So from that, how would you ascertain the current density J? Well, J is always the current that's uniformly distributed over the area, and in our case, it's in the AZ direction, right? They give it, what's A? Now, believe it or not, this one, sometimes people will mess up. What is the area in the shaded region?
Pi times b squared minus a squared.
That's right. It's pi b squared would be the total area. Pi b squared would be the total area there. Then you subtract off the inner core pi a squared. Or J itself becomes I over pi, and it's going to be b squared minus a squared. You're absolutely right. With me on that? That would be amps per meter in the Z direction. Do you agree with that?
Yeah.
Amps per meter squared.
Amps per meter squared. Everybody with me? Now, we think about this when we do our anterior loop business. Now, I'm going to ask to see how you guys do. First, for rho less than A, you know we have the integral of H dot dl over the closed loop is equal to the current enclosed, right? How much current is enclosed if I'm here, inside?
0.
So what's the H field?
0.
Does everybody follow me on that?
Yeah.
It is. So for rho equals A, really H, without doing the integral, H phi is 0. Now for rho greater than A but less than B. I'm going to give you a second. So now, I'm not here, right? Now I'm here. I'm somewhere between these two, right? So, and I need H dot dl equal to the current enclosed. So how do we get that? Well, the integral of H dot dl around that closed loop is still going to be 2 pi rho H phi. Do you all agree with that?
Is there any case where it wouldn't be 2 pi rho h p that we
Remember the infinite flat plane that I just showed you?
Okay, yeah.
Yeah.
Other than those two, are there any other cases we're going to use in this class?
I mean, not that we're going to talk about. There's 10 separable coordinate systems, okay? Now, you can get the egg-shaped proloids. You can do a whole lot of weird things with these, but that's way beyond anything we're going to cover you. That's graduate level. That's actually doctoral level. Back to this thing. You all agree that that's true, right? What about how much current is enclosed? Well, the current density is a constant, right? So really what I need to do is figure out a way to estimate the amount of area that's there. If I take the area times the current density, it's not even an estimate, it's an exact thing. What am I going to do? Technically, I do this. I take a double integral of J, right? Since it's a constant. Now, I mean, it doesn't have to be AZ, and then it's going to be times the differential surface vector, which is rho d phi d rho. Here, phi goes from 0 to 2 pi, and rho goes from A to rho. And technically, what I need to do is prime it. But you all follow me on this, class? Take the current density, and this should be an AZ, and it should be a dot product there, so the AZs will go away. And when you integrate this, well, JZ is a constant, it can come out in front. You really are integrating the area, and that would be, when we go rho d phi, we get rho times 2 pi. And then when we integrate d rho, we're going to get rho squared over 2, or we end up getting just pi, and it's going to be rho squared minus a squared. So that means, for this case, I'm kind of crowding myself, but for over here, I'm going to put it more in the center of the board. Okay, so now I have for rho greater than A, less than B, I have 2 pi rho h phi on this side, and it's equal to, on this part of the integration, since jz is a constant, I'll just take it up the front, and that's equal to I over pi, and here it's b squared minus a squared, and then it's times the area, and that's area is going to be pi, and it's going to be rho squared minus a squared. You all follow me on that? Take a moment, make sure you do. Okay. Ready? Okay. So, that means h phi is what? H phi here is going to be, you can cancel that, right? So I'm going to get 1 over 2 pi rho, and it's going to be times, I over 2 pi rho there, and then it's going to be rho squared minus a squared over rho squared plus, or over, sorry, b squared minus a squared. And if you look at that, when rho is equal to b, then you get just I over 2 pi rho, or 1 over I over 2 pi b, right? Because these two will can't, it'll be 1 and 1, right? But when rho is equal to a, you'll notice this goes to 0. With me, class? So I can say, at least for the, between a and b, this is it. And it's got an odd kind of shape, but it's not hard to actually track the shape. It starts at 0 at rho equal a, and it goes to I over 2 pi b at rho equals b, and it does it in kind of a, what do you call it, this is a weighted, it's really a bent line. It's not exactly straight, but there's not a whole lot of bend to it. I'll try to draw this in a second. Next, finally, what happens, what is h phi for when rho is greater than the outer radius b? What is h phi? Anybody could tell me how to get it? I want to see. How do we get it?
Instead, you integrate, you do the same, but you integrate from A to B.
Always start by thinking this way. I'm going to integrate H dot DL around the closed loop. That's equal to the I enclosed, right?
Yep.
We could write, but what is this?
2 pi rho HV.
Do y'all agree with that? What's on the other side? How much I is now enclosed by our loop? Think about it.
All of it.
Oh, that's right.
Oh, so
Now
it's
we're
just
outside here. It's all of it. It's just I, right? It's just I, which means H feet out there is simply going to be I over 2 pi rho. And it would be in the AV direction, of course. And that's amps per meter. So if you plot it, what is it going to look like? Plot here. I think you guys are getting the hang of this. Plot it for me. I ask people to sketch things all the time like this. Okay, at 0 it's 0 until I hit
A.
and then it starts going up, right? And it's going to go up. If you look at this is hard to see. This is actually, if you divide through by rho, you get rho minus A over rho. Do you all follow me? If you divide through by that. So rho minus A over rho. It's really doing one of these things. Sort of like this. It's hard for me to draw it exactly, but it looks sort of out there. It's doing this. And then it hits here, and then it's going to fall off as 1 over rho. So this point right here will be I over 2 pi rho as far as H feet. Do y'all agree with that? I mean 2 pi B, right? Would be the height. And that's what it will look like. Now, what I typically do, as you're getting to know me, suppose I give you a current density. I'm going to give you a current density. And I ask you for the H field between, to plot the thing out. Suppose I gave you a current density, then what you would have to do is what? This integral here, Jz may not be a constant. And if Jz is a constant, then you're going to have to do that integral, choose your function radial distance. Okay? That's the one thing. You all know why I'm saying that, because on the prior exam for the capacitance, I think even for resistance, a lot of people just kind of memorized what the capacitance or resistance was for constant conductivity or constant permittivity. Well, here, if I give you J that it is non-constant, you should be able to handle that problem. All right? And I can come up with some right now, but I think you understand, right? Okay, you got another one for me, or can I? All of them are going to be the same type of problem.
We can, but
I think I would.
I would like to do, now in the next section in the book, he's going to be talking about getting getting J from the H field, and that is, 1 second. That's section 4.4. And this is just one of these things. Just look at the definitions of the curl. The only thing we can do on it is really, I think it's as straightforward as it gets. I thought you were wrong about this, but if you look at this, here's the law. Curl of H is equal to J. The curl is defined in the back of your textbook on the inside cover of the book. Y'all follow? So, if it's I'm not going to expect you to memorize that. I will give you the curl. But you should have it, by the time the final exam comes, you should be able to do the curl in Cartesian. So if you look at curl of H, and we're in Cartesian coordinates, I like doing it this way. It's AX, AY, AZ. And then you put HX, HY. Sorry, my bad. Then you put the derivative with respect to X, derivative with respect to Y, derivative with respect to Z. And then you put HX, HY, HZ. I don't know if he has this formula in the back of the book or not. I actually forgot if he does. Yeah, he does. But I want to tell you one thing. In his book, you see, if you look at the back cover of the book, you'll see me right here. If you look at this, see how it says cylindrical? He's got the Cartesian variation of that in mind. Is yours? See how that is X, Y, and Z for cylindrical? Cartesian, cylindrical coordinates are rho, P, and Z. So he messed that up.
For which one? The curl for?
Yeah. Hey, I want to make sure you see this.
Yes.
So it says cylinder, there's not, that's Cartesian. He messed that up. Same as this. He doesn't have the right form for cylindrical.
Okay, will you provide it for your
Absolutely.
Minus rho. Would this be right? Oh wait, no. Yep, for curl. Is that right? For
Yeah,
cylindrical?
that is, but that's a newer version. His older book.
Gotcha.
Mine is just like yours.
Okay, it's messed up. So I'm trying to warn you about that because that is wrong, obviously. But I'll provide you that information. This is the one you should know, and if you look at this, you're already doing it. But what happens? You have AX, right? Remember how to do these from linear algebra? Take this, and then I go this way, so it's d dy of hz. Right? And then, if you take it this way, and there's AX here, it's minus ddz of hy. I'll show you the trick to this. Plus ay, bless you. So when we get ay, come down here, that's going to be d dz of hx minus d dx of hz and plus az here. And for az, it's going to be d dx of hy minus d dy of hx. Something to note here. Anytime you're talking, this would be the curl of h in Cartesian coordinates. Once you establish what component you want, these derivatives and field values will not have that component. And if you get the first one, if you take, like, the first one is dhz dy, you'll notice the next one is the same exact form, only you flip it. Now this becomes hy, and this becomes ddz. In other words, there's a very predictable manner to this thing, to doing the derivatives. So that would be the curl in Cartesian coordinates. For his, does he give a problem in the back? I almost think it's too trivial, but if you look at part A on problem 4.24, he has 3xy squared over z. And it doesn't matter if you call it a, y, but he calls it a. So a is equal to 3xy squared over z, I forgot what direction it's in. And the ax direction he should have put h there, but it's fine. So if you're applying a curl to this, what is it going to be? What is the curl of a by definition? Just have a look. All right, this is, technically it's like, this is like hx, right? Forget that, right? Y'all follow me? I'm saying, he says a, it's in the x direction. I'm putting hx. I'm just trying to make sure.
Are hy and hz 0?
Well, yeah, before you, let's go through this. So if this is hx, the only thing you care about are things that have hx in them, right? There's nothing here, right? This has hx right here, right? And this has hx right here, correct? Well, this is hx, that's hx. Y'all see me? See this? So if I take the derivative, if I want the curl of this, that's AY is the vector sense. Now, the derivative of HX with respect to Z is what?
Minus 3.
I'm going to put 3xy squared first, right? Because they're unaffected by a derivative with respect to Z, right? And then I take a derivative of 1 over Z. That's what?
Minus 1
over Z. Minus 1 over Z squared, correct? So it's going to be that, and I can put a minus sign right here over Z squared. And then it's minus, there's no HZ, right? Only an HX, see it right here? So that term goes away. This term would be minus 3xy squared, would be in the AY direction. And then I have to say plus AZ. And then I have to take a derivative of HX with respect to Y. And what is it? Am I looking?
6xy over z.
That's right. And that's, I'm just telling you, that's as simple as it gets with this stuff. It's a bunch of derivatives that you're going to have to execute properly using the right equations. Now, he has spherical in the back that's correct in my book, I think.
Mine's correct.
Yeah, he does, and he has it in terms of a matrix. He expands it. Be careful of that expansion. I haven't checked that, but the matrix he has there is right. So that said, it's kind of a no-brainer. If you're given the H field you want for J at that point to cause, you simply take a curl. Everybody with me? There's not much. It's like if you're given D and you want the charge density, divergence of D. This is the same thing. If you're given H and you want J, you take a curl instead of divergence.
It's right on page 615.
What is it?
It has the cylindrical curl.
Okay, on page what?
615.
I don't know.
I just opened a random page and it was there.
Miracle.
It's got other relations on the backs.
I'm glad you found it. $6.15, you said?
15, yes. Mine's right.
Yep. Yeah, it's right there. Good. I'm glad you saw it. Miracle.
Yeah, no, that was a complete accident.
That's all right. Every God's trying to tell us that's the right one. Okay. What's the next one?
Next one is what?
I tell you what. I'm getting out of time. Those things, in my opinion, are very straightforward. You should be able to execute any kind of derivatives based on the formulas. So I'm not going to, and I'll give you the formulas, basically the curls if I'm asking for them. All right, so that's not really a challenge. Now, hold on. That's section 4.4 in a nutshell. I want to talk about, I put this up here already with, I said that what Stokes' theorem is, this is equations 4.29 really, and it defines the curl specifically, don't worry about that. This is on page 236. Next thing it talks about is magnetic flux density that I was mentioning, so I'm going to talk about that for a second. Now we always talk about electric flux and the magnetic flux. So, you remember when we talked about electric flux, what we said is the integral of B dot ds over a surface was actually the flux penetrating that surface. Do you all remember that? And if it was over a closed surface, then it's the charge enclosed. Well, for the magnetic flux, it's the integral of B dot ds over a surface is called the magnetic flux. And that's all this is. This is magnetic flux. And it's in terms of Webers. Flux density, B is Webers per meter squared. You integrate it over a surface, you get Webers.
What's the units for electric flux?
Electric flux here is going to be coulombs, because you're integrating coulombs per meter squared times meter squared is coulombs. But this is magnetic flux. So B, again, is equal to mu times H, and the mu is mu relative times mu naught. Mu naught is, this is from measurements, is 4 pi times 10 to the minus 7th. And this is going to be henries per meter. So, that's all well and good. We're going to see we use this term flux a lot when we calculate inductance. Now, something that's real important to note is if you take the integral over any closed surface of B dot ds, you get 0. If you take a look at the point form of this, well, the integral over the closed surface of B dot ds over the closed surface is the same thing as the integral. This is another theorem. The divergence of B ds, or I mean over the volume, d vol, and that means divergence of B is 0. This is real important when it's on here. If you come over here, and you come from that, and you know that divergence of D is rho V, right? Y'all remember that?
Yep.
Now that's the electric charge density, right? Divergence of D is rho V. What this is telling you in an indirect way is there's no magnetic monopoles. There's no magnetic things that have a single positive or a single negative charge. They always come in dipole pairs. It means anytime you're talking about magnetism, self-magnetism, you would have these extremely small, indistinguishable small, there'll be dipoles where you're going to have a plus minus theoretical magnetic charge that creates it. But you can't separate out the magnetic charge that's positive from the negative. Do y'all follow me on that? Now, do you remember this from physics or not? Divergence of D, or B is 0. Anybody?
I didn't use divergence physics.
So, the thing that what it really means is there's technically no magnetic monopoles. There's no single peak. You can't find just plus magnetic charge and negative. Well, at the macroscopic levels, now I've been told this and I'll just have to take the word for it. There's a thing in Europe called the supercollider superconducting system, and they take particles and they smash them up. They're called atom smashers. And then they look in these vapor chambers for the aftermath, what comes out. And they have detected at very small time intervals with very high energy where they can actually get a theoretical magnetic charge, and that's positive or negative. But the existence of it is, it's gone as that fast. It just basically, as soon as it's separated, goes back together. I don't know, pretend to know all the things that happen, but there is, in physics, some theoretical, I guess, well, I shouldn't say that. There is a possibility of a magnetic charge, monopoles of magnetic charge, to exist under extreme conditions. Now, when I say extreme conditions, it's not the temperature of the sun. It's much, much higher. It's ridiculously hard to get the amount of energy in a molecule to have that actually happen, or I should say at the center of the atom. So I'm just telling you that so you know. It's something we don't talk about here. Divergence of B for anything we care about is 0. Now, So I said that. Now, in his book, if you have the book, look at page 239 for a second. At the bottom, I want to just contrast this one thing. You see how he has the integral form, and then, I don't know if he calls it differential form of the laws, right? It's got Gauss's law first, integral of d dot ds is charge, is q enclosed, differential div d is rho v. Second one, integral of b dot ds is 0. That's the actual flux. It means divergence of b is 0. Then integral of e dot dl over a closed loop is 0, means curl of E is 0. This we call it conservative field. And that's only true for electrostatics, by the way, not magnetics. I mean, not when we get into a time varying or electrodynamics. Next, the integral of h dot dl over closed surfaces is I, and the differential form of that is curl of h is j. So those are the laws for electrostatics in the integral and the differential form, and those are the ones you should always kind of look at if you have any questions. Next, he's going to talk about magnetic forces. Now, I'm going to do justice to this. I'm going to start this talk. Now, you had magnetic forces in physics, didn't you?
I did, yes.
You remember?
I don't think I did.
You had electrostatic forces, QE, right? Magnetic forces, I guarantee you probably. Did you ever physics here?
Yeah, I don't know. Mine was over Zoom, so it was like, I don't know if we covered everything we were supposed to.
You had to cover that. That's core. It's like F equal ma kind of stuff.
Yeah.
If you're a physicist, if you're taking general physics at college level, then you're going to get this. So anyway, here's what it amounts to. If you have, and I'm going to start with the current element. If you have a current element and it's I dl, and when you got a current and it's got a vector sense to it, it's a differential link. There's going to be a force on it, right? A differential force. And it's assuming it's in the presence of a B field. And the differential force is equal to I dl crossed into B. That's the differential force. Y'all follow me? It's a real important concept. Now, one thing about this is the force is always perpendicular to both the direction of current and the B field. So let me try to make it real to you. If I have a current element this way, say this is my differential current, it's flowing that way, and I have a B field this way. Let me try to give you an idea. So current flowing this way, B field this way. The force IDL crossed into B, IDL, right, crossed into B would be that way. Y'all follow me? So it's perpendicular to the B field, IDL cross B would be this way. Am I done? You're making me feel like I'm done.
It's just like the bus leaves, like,
Oh, never mind.
yeah, I don't want to miss the bus.
All right, where you gotta go? No, I mean, that stop over there by the stadium?
Yeah, the farthest one. But yeah.
All right. Here's the deal, guys. I'll pick it up there next time, and for the quiz, it's gonna be on materials that we talked about up through, not the flux and not the, in other words, it's going to be on Ampere's law applied. I hope I made it clear.
The quiz, Ampere's law. Yes, sir.
All right, guys. Thanks for doing that. I'm beat.